Of the complex fractions. Partial fractions come in 1050.
Wait, what's partial fractions?
Partial fraction decomposition.
It's where you break a fraction into its parts. It's actually kind of a cool process. Okay, so let's not. Okay, in this section we're going to go over applications of quadratics, which means we're going to be doing story problems. On the front we've got 3 story problems. On the back there are 2, and then I've got one more that I'm going to show you at the end. There's is that, yep, Dwight Howard. Okay, yeah, it's in color too. Okay, so if you've been paying attention and doing these problems the way I asked you to, the setup for these problems is no different. Okay, everything is pretty much the same. We're going to approach the problem the same way. I am going to show you a different technique that you can solve these particular problems, so take a look here. During the first part of a trip, Tara's Honda traveled 120 miles at a certain speed. Then Tara drove another 100 miles at a speed that was 10 miles per hour slower. If the total time of Tara's trip was 4 hours, what was her speed on each part of the trip? So because we're talking about distance, how fast she was going, how long it took her to go that far, and all that sort of stuff, we're going to keep track of it this way. We're going to do distance, rate, and time. And then we're going to come up with a formula D equals RT for each part of her trip. So let's see. On the first part, she traveled 120 miles. That was her distance. At a certain speed. Do we know what that speed was? We don't. So what do you want to use to represent it? We could use X. That's a little bit of a generic variable. We could use H for Honda. Okay. How about this? How about we use S for speed? Okay, that's her speed. I do lack creativity. That is a true statement. Okay. Tara then drove. Okay, so we're now on the second part of the trip. Tara then drove another 100 miles. Okay, so this is on the second part of the trip. She drove 100 miles at a speed that was 10 miles per hour slower. 10 miles per hour slower. Well, we didn't know what this one was. We used S to represent it. We do know something about this speed. It was slower. How much slower? Okay, so if we wanted to use a totally different variable, we could, but since we've already got an S for this one, how do we represent 10 miles per hour slower than S? Okay, it does have to be S minus 10. It can't be 10 minus S. Okay? Speed here, speed subtract 10 here. Okay, if this was 90, this would be 80. I don't advocate going 90 though. Okay? Any questions? Okay, so that takes care of the first sentence and the second sentence, and then let's take a look at the end here. If the total time of Tara's trip was 4 hours, what was her speed on each part of the trip? So they're asking how fast was she going on the first part and how fast was she going on the second part. But this last piece of information says that the total time of the trip was 4 hours. So there are 2 ways to do this. Okay, I'm going to do it this way to start with. Let's say this one is T. We don't know how much time she was going 120, how long it took her to go 120 miles. So we're going to use T to represent that. If the total time was 4 hours, how could we represent this one right here? Sarah says 4 minus T. 4 minus T. Let's take a look at that. So if we said this is 4 minus T, let's see if that notation works out. If this is 2 and the total time was 4, how much time should this one be? Should be 2. 4 minus 2 is 2. If this is 1, let me mark it down here. If this is 1, how much should this be? 3. 4 minus 1 is 3. So does this notation work? Okay, that's one way to do it. Okay, I'm going to finish that problem this way, then I'm going to show you a different way to do it. So once we get these 3 boxes filled out, this is distance, this is rate, this is time, I write equations. 120 equals S times T. 100 equals S minus 10 times 4 minus T. Okay, then I look at this and I say, all right, look at the 2 of these equations. Okay, pick a variable that's fairly easy to solve for. Of these 2 equations, which one's the easiest to work with? Probably this one right here. Okay, what variable do you want to solve for? Let's solve for t. So this is going to be t equals 120 over s. If I solved this one for t, let's solve this one for t also. So the easiest thing to do here is let's get rid of the s minus 10. So this is going to be 100 over s minus 10 equals 4 minus t. Okay, and then I'm going to do something a little bit tricky. See that negative? I don't really like that. Okay, so I'm going to move, you could move the 4 to the other side and then multiply everything by a negative. That would actually work pretty well. Okay, or I can switch sides with the two of these. So I can do t equals 4 minus 100 over s minus 10. Everybody good with that? There's t equals this stuff. There's t equals this stuff. So if t equals 120 over s and t equals 4 minus 100 over s minus 10, what can I do with these two equations? Set them equal to each other. So I get 120 over s equals 4 minus 100 over s minus 10. Now, once I get to this point, okay, I'm going to stop right here for just a second. Once I get to this point, I can actually ignore the rest of the problem because this is just a rational equation. Distance, rate, and time, set up my equations, solve the equations each for a variable. I'm basically solving this system by substitution, right? I could have solved for s here, okay, and plugged in and set these two equal. I'd have t's over here, okay? But this is actually the best choice for a couple of reasons. Okay, they usually ask us questions in this way, and it says, what was her speed? When I get done solving this, I'm going to have an S, right? What did S stand for? Speed. Okay, any questions? Everybody understand it there? Okay, then we're going to finish solving this. So to finish solving this, this is a rational equation. I don't like working with fractions unless I absolutely have to. People are prone to make mistakes. So what we're going to do is we're going to multiply by something that will cancel off an S and an s minus 10. So I need to multiply by s and s minus 10. If I do that here, I have 120 times s minus 10. What happens here? Does anything cancel? No. So this is 4s, s minus 10. And what happens here? The s minus 10 cancels, so there's 100 left and an s. Now, at this point, I can just solve this just as I would any other quadratic. Okay, maybe not that big. So this is going to be 120s minus 1200. Over here, I get, careful here, 4s squared minus 40s minus 100s. And then I'm just collecting like terms, setting it equal to 0 and all that sort of stuff. Now, on this particular problem, am I going to move everything over to the left like we usually do, or should I move everything over to the right? Let's move everything over to the right. If I move it to the right, that leaves me with a positive s squared. So I'm going to subtract 120s, and I'm going to add 1200. So add 1200. So let's see what I get here. I get 0 on this side, 4s squared, and let's see, these are all s's. So I get negative 260, is that right? And then plus 1200. Now, this is kind of an ugly problem, fairly big numbers. Yeah.
I don't think 260 is right. I think it's 160. No, it's not.
No, because this is a minus 120s, that's a minus 40s, that's also a minus 100s. So these three are all like terms. That one, and that one. Does that work? We doing okay? Any mistakes? Okay, at this point, it's a quadratic. You can solve it by factoring. You can solve it by completing the square. You can solve it using the quadratic formula. What do you want to use?
Not the quadratic formula.
Okay, the first thing I'd do is let's make this a little bit easier. Let's get rid of the 4. 4 goes into all of those, doesn't it? It does.
Yes.
So if I divide everything by 4, I get s squared. If I divide that by 4, I get, let's see, 65, negative 65s. And then if I divide this by 4, I get 300. Holy cow, look at these numbers. I need numbers that multiply to be 300 that combine to be 65. Think about that for just a second. Let's cover this up and say it was a 30. What multiplies to be 30? 6 and 5. So if you add a 0 to one of those and make one 60 or 50, okay, we could probably come close to a 65. What numbers am I going to use? Okay, I'm going to use 60 and 5. They're both going to be negative because that'll make it multiply to be a positive and combine to be negative 65. This says s equals 60. This one says s equals 5. Now, we were solving a quadratic. Haven't even thought about the story problem in just a bit. Let's see. If that's 5, this would be negative 5. Does that make any sense? No, because we're talking how fast the car is going. Certainly can't be negative. If this was 60, this would be 50. Does that make sense? It does. So how fast on either part of the trip? 60 on the first part, 50 on the second part. Okay? Everybody see that? Any questions? Okay. I'm going to show you a different technique, same type of problem, okay, but it's a different way to solve the same thing. Everybody ready? Okay, can I slide this down? Okay, I'm gonna leave that much there just so we can see it. So on this one it says, during the first part of a canoe trip, Ken covered 60 kilometers at a certain speed. He then traveled 24 kilometers at a speed that was 4 kilometers slower. Gosh, that's almost exactly the same thing, except for Ken, for some reason, is in a canoe. What's her name? Tara was in a Honda. That's much better. Okay, so let's do the same thing. Distance, rate, time. We're going to keep track of the first part and the second part. And then we're going to come up with D equals RT. Okay, during the first part, 60 kilometers at a certain speed. We don't know what it is. I'm going to go ahead and use R here for the rate. Then he traveled 24 kilometers at a speed that was 4 kilometers per hour slower. Well, that's pretty easy. If this was R, this is going to be R minus 4. Again, it's got to be R minus 4. It can't be 4 minus R. If the total time of the trip was 8 hours, what was the speed on each part of the trip? Okay. Well, here we said, well, let's see, if this one was t, this would be 4 minus t. That was if it was 4 hours. So if I did a t here, I'd do, since the total was 8, I'd do 8 minus t here. And then we could solve it the same way we did the other one. Okay, I'm not going to do that. You ready? Okay, I'm going to say this. I'm going to say t1 was the time on the first part of the trip. And I'm going to say t2 was the time on the second part of the trip. Let me write this equation. 60 equals R times T1. Oops. 24 equals R minus 4 times T2. Now take a good look there. How many variables are there? Take a good look. 3. R is the same in both of them, but this is the time on the first one and this is the time on the second one. Those subscripts mean those are different values for T. Okay, so those are different. So I actually have 3 variables and they only have 2 equations. I can't solve 2 equations with 3 variables. Remember we solved these, I think in chapter 3. If I have 3 equations and 3 variables, then I could. So here's the trick. Remember we said the total time was 8? So that means if you take the first time and the second time and add them together, you get 8. Now really this amounts to the same thing. I want you to look at how similar this is. Which of these variables would be the easiest to solve for, the R's or the T's? R and T are about the same here, but look at this one. By far, T2 is the easiest one to solve for. So let's do 60 over R equals T1. On this one, we're going to do 24 over R minus 4 equals T2. And look, here's a T1, there's a T1. Here's a T2, there's a T2. So I should be able to take these and do what with them? Add these together and set it equal to 8. So this is going to be, let's see, 60 over r plus 24 over r minus 4 equals 8. Okay, now take a good look right here and right here. Okay, and I'm going to make this smaller, okay? So we can see the whole thing. Okay, this is how much work it took to make that equation. This is how much work it took to make that equation. So does it look like it's about the same amount of work? Okay, it does not make any difference how you solve it, but I would definitely continue to set it up this way. If you want to write this extra equation here, the T1 plus the T2, that's fine. In some respects, this is pretty easy to solve for and then plug it in. Okay, in other respects, the fact that we didn't have to introduce another variable like T1 and T2, we just did it in terms of S and T. But you do have to remember to write this as 4 minus T, 8 minus T. If it was 10 hours, it would be 10 minus T. Okay, and then solve for T in each one of them. Okay, are there any questions? Sure? Okay, let's go ahead and finish this one. Let's go ahead and do this real quick. We're going to get rid of this by multiplying by r and r minus 4. So this is 60 times r minus 4. This is 24r. And over on the other side is 8r and r minus 4. You'll notice that we still have variables on both sides of the equation regardless of what we do here. So let's see, 60r minus 240, and you just need to be careful with these, plus 24r, and then I have 8r squared minus 32r. Did I do that right? Which side are we going to get everything on?
The right.
We're going to get it on the right side. So this is going to be 0 equals. Okay, I'm going to subtract 60 and subtract, add 24r. And then I'm going to add 240. So this is what I get. 8r squared. That was an r. Let's see. That'd be 92. Negative 92 plus 24. 92 minus 24 is, I think it's 78, isn't it? What was that?
So, wait, how do we get the plus 24r if it's a...
Oh, it should be minus, shouldn't it?
Yeah.
Yep, thanks. They're all negative. Yep, yeah, those two are positive, so those are negative. Excellent. Okay, so we've got negative 92 and then another 24, so that's going to be 116. So negative 116 r and then plus 240. Okay, everybody good to there? If we're lucky, we can take out an 8. Can we take out an 8? Can't take out an 8. Okay, 8 goes in here and 8 goes in there. Doesn't go into 116. We can take out a 4 though. Let's go ahead and take out a 4. So divide everything by 4. You get 2r squared, negative 58r, and then this would be plus 120. Do you want to try and factor that? If you want to try and factor it, go right ahead. But the quadratic formula... Did I make a mistake?
Well, we could also take out a 2, if that's all correct.
Oh, let's see.
59.
Oh, 50.
9.
No, this should be 58. Let's see.
Wait.
No, it doesn't. Let's see.
Wait a minute.
I took out a 4, so this should be smaller. So that should be, let's see, 29?
No, that makes more sense.
Okay, that's better. Okay, you're right. Let's see. So those are as small as we can get them. If you want to try and factor, we'd have to come up with numbers that multiply to be 240 that combine to be negative 29. You can rack your brain about that for a while. I bet we could figure out some that do. Oh, this is 60. Man, would you guys keep me on my toes? 60, there we go. Okay, there's 120. I must have been thinking divide the first one by 4 and divide the other ones by 2. That's nice. Okay, So can we come up with numbers that multiply to be 120 that combine to be negative 29? Don't 24 and 5 work?
Yes.
24 and 5 would do it. So you can factor it using those. You can also use the quadratic formula. It wouldn't be that bad to plug it into the quadratic formula, especially since you get to type it into your calculator. So you'd have 29 plus or minus 29 squared minus 4 times 2 times, good thing we got these numbers right now, okay, all over 2a, so 4. And you could type that into your calculator. It may be that the one with the plus gives you the correct answer. It may be the one with the minus does. Let's go ahead and factor this. Let's see. And they both need to be negative, right? Because that gives us a minus 5r, that gives us a minus 24r, so there's our negative 29r. So the answer that comes from here is 5/2, and the answer that comes from here is 12. Which one is it? Why does it have to be the 12? Okay, because if this was just 2.5, that's what this is. This would be 2.5, this would be 2.5 minus 4, so that'd be negative 1.5, and again, that wouldn't make any sense. So this has got to be 12, this has got to be 8. What were the times then? It doesn't ask for that, but what were the times? How many times does 12 go into 60? 5. How many times does 8 go into 24? 3. So he was going 8 miles per hour or 8 kilometers per hour for 3 hours. There's the 24 kilometers. 12 kilometers per hour for 5 hours. There's the 60 kilometers. Okay? Make sense? Okay. More familiar looking problems. Filling a pool. It says a well and a spring are filling a swimming pool. Together they can fill the pool in 3 hours. The well, working alone, can fill the pool in 8 hours less time than the spring. How long would it take? The spring take working alone to fill the pool? Okay, so this is, a similar problem to what we've done before, but you'll notice they didn't tell us how long it took the spring or the well to fill this up. Okay, they told us how long it takes together, and then they gave us a comparison of the two. So let's keep track of it this way. We've got a well, we've got a spring, and then we've got together. So this is the well, this is the spring, and then we've got together. And we keep track of what fraction they do, how long it takes them and what fraction they can do per hour. So it says, let's see, the well can fill the pool in, they can fill it together in 3 hours. The well working alone can fill the pool in 3 hours less than the spring. 8 hours less, thanks. 8 hours less. Let's see. The well, working alone, so the well can fill the pool in 8 hours less time than the spring. So if we knew what the spring was, we could say what the well was. Let's use S for spring. How can we represent the well? Okay, it's 8 hours less time, so we're going to do S minus 8. And again, just like before, it's got to be S minus 8 rather than 8 minus S. Okay? Everybody okay with that? Okay, watch please. Do you see why setting this one up this way kind of sets us up for down here, how we do something like this? We're going to take the big one, subtract that small one. So we're going to take the spring, subtract the 8. That's what's going to be left. Just like if we had 4 hours total, we're going to subtract the time that we already used. Okay, and from there on, it's just reciprocals. So if we gave that 1 hour, it would be a third of the job done. That would be 1 over S, and that would be 1 over S minus 8. So once you figure out these expressions, it's exactly like we did the problems before. So I'm going to take 1 over S minus 8 plus 1 over S, and that should equal 1 over 3. So this is the fraction the well does. This is the fraction the spring does, and this is the fraction that they do together in 1 hour. So notice we're doing what the well can do in terms of how fast the spring works. And then from there, it's just multiply by s, and s minus 8, and in this case, 3. So that's going to give us a 3s. That's going to give us a 3 and an s minus 8. Make that look like an s. And over here, that's going to give us an s and an s minus 8. Now, at this point, I'm not going to finish that. I think you can finish that. Okay, they're basically all the same. Look at these equations that we've come up with. Okay. All right. Any questions? Sure? Okay. Those are the difficult types of problems. You do have some problems on your assignment where they actually give you a quadratic equation. You just need to know what to do with it. Okay, so it says, let's see, an object tossed downward with an initial speed, or in other words, a velocity of v naught, will travel a distance of s meters, where s is equal to 4.9 t squared plus v naught t, and t is measured in seconds. Solve for t. So it tells us we want to solve for t. This is a whole bunch of information. This is just how far. It's a distance. 4.9 t squared, that stands for time, plus v naught, that's called the initial velocity. In other words, that's how fast it was going to begin with. And again, a t, that stands for time. So we're going to use this in order to answer these questions. So it says, a bolt falls off an airplane at an altitude of 500 meters. Approximately how long does it take the bolt to reach the ground? Well, let's see. If it falls off, what was its initial velocity? Yeah, that means v naught is equal to 0. So if we take a look at this formula right here, 4.9 t squared plus, v naught, so that's going to be 0 times t equals s. Here's our formula. 4.9 t squared equals s. That's it. Approximately how long does it take the bolt to reach the ground? Well, let's see. If it fell off the airplane right here and fell down to the ground, how far did it fall? 500 meters. So that's the distance. So we're going to do 4.9 t squared equals 500. Divide by 4.9. Why am I not bothering factoring or anything like that, or setting it equal to 0? Can anybody tell me why I don't set it equal to 0 and factor it, or use the quadratic formula? It's got one variable term, and it happens to be a perfect square. So remember, if you can solve a quadratic by taking a square root, that's the easiest way to do it. So if there's a plain old perfect square, which there is right here, I can get that by itself by dividing by 4.9, and then I take the square root. So I get t equals the square root of 500 over 4.9, and luckily we're going to use a calculator for that. Why do I not have to put a plus or minus on there? Yeah, the t stands for time, okay? So we'll throw that in the calculator. So that's going to be the square root of 500 divided by 4.9. So about 10 seconds. 10.1. 10.1 seconds. There's the answer to the first part. Okay, if the ball is thrown downward with a speed of 30 meters per second from an altitude of 500, approximately how long does it take to reach the ground? So it's going to get there faster because we threw it down, we didn't drop it. Okay, if we threw it down, what is this right here in these formulas? V naught. Okay, so V naught is 30. So our formula now becomes 4.9 t squared plus 30t equals s. And what do we want s to be if it still fell or was thrown down 500 meters? We want that to be 500. So 4.9 t squared, 30t equals 500. How would I solve this? No, because that 10.1 seconds was if it just dropped, we threw it. Okay, we're going to have to set this equal to 0. We're going to have to go through and solve this like a legitimate quadratic equation. Do you want to try and factor that?
Not really.
No, so let's use the quadratic formula. Again, if you set it up right and have your calculator do the work for you, it's not that bad. So this is going to be negative 30 plus or minus 30 squared minus 4 times a times c. Again, we don't want to skip this part. So this is going to be 4.9 negative 500 all over 2a, so that's going to be 9.8. Okay, did I set this up right? Did I identify a, b, and c correctly? Did I make any silly sign errors or anything like that? Didn't divide one thing by 2 and divide the other thing by 4? That's just crazy. Good? So the only part that you could screw this up now is if you plug it into your calculator wrong. So let's make sure we type it in correctly. Now, you'll notice the top has several terms. Let's go ahead and start off by putting that in parentheses, because if we put parentheses, it'll take the entire top and then divide it by the bottom. So this is going to be negative 30. Then I'm going to do the plus first. Start the square root. I can type in 30 and square it. Negative 4 times 4.9 times negative 500. And again, there's a difference between the negative and the minus. Make sure you get that straight. I've got to close the parentheses there. Then I've got to close it again because I opened them here, opened them again for the square root, close the square root, and then close the top. Good? Hit divide. If I needed to do 2 times 4.9, I'd put it in parentheses. Okay? We know that's 9.8, so I just wrote it there. I would know how to do it this way. Any questions? Okay, let's hit enter, see what the answer is. It says 7.49. 7.49 what? Okay, now just to double check, let's see what would happen if I recalled that, or you hit the up arrow on one of those scientific calculators and change that to a minus. So this is a minus here, and we're going to be subtracting something, so we get negative 13.6. Why doesn't that make any sense?
Because you're going back in time.
Yeah, it stands for time. You'd be going back in time. Okay, so we get x equals 7 point what? 4 what? 494, and that's going to be in seconds. So there's the answer. Okay, watch please. Just to keep you on your toes. Okay, if we throw this down, this is actually a parabola. Okay. So this would be like it hits at 7.494 seconds. Going back in time, instead of going down, it would have been going up and then come down and hit over here. It would have hit at negative 13 point whatever seconds. Okay? Just kind of think about that for a second. Okay, and then let's take a look at this one right here. This is number 35. Bungee jumping. Chad is tied to one end of a 40-meter elasticized bungee cord. Okay? The other end of the cord is tied to the middle of a bridge. If Chad jumps off the bridge, for how long will he fall before the cord begins to stretch? So don't say anything out loud here. It gives us the equation right there. It says 4.9 t squared equals s. Where did the v naught t go? Where did the initial velocity times time go on this particular one?
Well, since he never touched the ground, so.
Not really. How fast was he going when he jumped off the bridge? Yeah, 0. Just like when the bolt fell off the airplane, it was falling at a rate of 0. It didn't have an initial velocity. Okay? So it's that simple. That's the equation. Yeah.
Did we do C for the last one?
Oh, we didn't. Okay, I'll come back and do that in just a second. Thanks, John. Okay. Let's see. So if it's 40 meters long, how far will he fall before it starts to stretch? 40 meters. So we take 4.9 t squared and set it equal to 40. And that's an easy one to solve because, again, we just divide both sides by 4.9 to get the perfect square by itself. So t would equal the square root of 40 divided by 4.9. Again, make sure you plug it into your calculator correctly. Okay, any questions there? Get that one and then one more. Okay, this one says approximately how far will an object fall in 5 seconds when it's thrown downward with an initial velocity of 30 meters per second from the plane? Okay, well this one is the formula that we used for it's falling and it had an initial velocity of 30 meters per second. So we'd use this one right here and this time it gives us the time. So what would we do with this? Yeah, you just do 4.9, 5 squared, plus 30 times 5. That would tell you how far it falls. And I'm going to make that look like an S, and I'll make those look like 5s. Okay? Any questions? Okay, last one. You don't have this on your paper, but it's pretty easy to do. It says Dwight Howard has a vertical leap of 38 inches. What is his hang time? So if you jump up in the air, your hang time is how long you're in the air. They usually use hang time for punts in the NFL and stuff like that. Okay, so we want to see how long he's in the air if he has a vertical leap of 38 inches. By the way, is that pretty good? That's pretty amazing. Over 20 is probably pretty good. That means he could jump up and his feet would probably be about right here. Okay, he can get himself pretty far off the ground. So this is V stands for the vertical leap, and T of course stands for time. Oops, make it look like that's not a 38. That's going to be time, and this is the vertical. So we're going to do 38 equals 48 T squared divided by 48. So we get 38 over 48. So again, this is one that you can just solve by taking the square root. So we get the square root of 38 over 48, which is, throw that in the calculator. Let's see what we get here. About 0.9 seconds. Okay, so even with that high a vertical leap, you're not even in the air for a second. Okay, so he's probably doing one of those dunks from the foul line or something. Still only in the air for about a second, a little less than a second. Okay, that's if he doesn't tuck his feet in a little bit. Okay, any questions? Okay, that is 8.4 then.